Thank you all and welcome to my project, SwimStat. So first off, I'm part of Gust. Here's a little bit about me. I have 4 years of engineering experience. Here at Grandview, I have my CSWE, which is the highest level certification in SolidWorks. Additionally, I have taken 2 computer science classes here at Grandview, AP Computer Science A and AP Computer Science Plus. Next year, I plan on majoring in either mechanical or electrical engineering at either Cal Poly or CU Boulder. Additionally, I swam for Grandview for 4 years. I'm the team captain this year. Additionally, I coached swim for 3 years and am applying to be a lead coach this summer for the summer swim team. Okay, so into my inspiration. So I have always loved swimming. I've always loved coaching, and I really like working and helping others with their technique, as well as improving just their swimming in general. I also wanted to learn more about new engineering disciplines such as coding and the electrical side, as most of the work that we've done here at Grandview has been focused in the mechanical department. Additionally, I was using a device called a tempo trainer in practice, which is ends up being similar to my project. However, it paces you while you swim. This, my device, is similar in design. However, it serves a completely different function, which I'll get into in a minute right now. So, so I wanted to design a device to collect swimmer data and send it to a computer where it could be interpreted. To create this and make it a reality, I needed a waterproof case to surround the device so that it didn't fry itself, blow up on the side of my head, whatever. Additionally, I wanted to create a computer program to interpret this data so that coaches can actually work with their swimmers to understand how many strokes, how many flips, how many breaths they took throughout the swim, and where they can work on to improve their efficiency in the water. Additionally, I wanted to display this information using a graphical user interface on the computer, which will allow the coaches to actually show the swimmers where they can improve. Next up, getting into my support advisors. So I first have Sharant Vaidar. He is my coding expert. And then next, Rudra Goel. He is doing a project with electrical components, so he's going on the same boat where we're both learning how to work through electrical and soldering, all that stuff together. And then Ryan Fritchell, he's great at additive manufacturing or 3D printing, as well as SolidWorks design. All of these aspects are crucial to my project, and they've helped me immensely. Additionally, I have Mia Wood as my expert advisor. She has a master's degree in engineering and technology from Colorado School of Mines, as well as she is a coach for a local club swim team. So getting into my logo designs, I created a logo with 2 S's, each representing swim and stat. The top one being the swimmer's arm stroke as he's breathing, as well as the water on the bottom. Additionally, the color, obviously it's swimming, so I went with the blue, which also represents control, which is something that I really want to focus on with this project, as it's working on the swimmer's technique and improvement. Additionally, it's a simple design so that I can print it on the bottom of my device, for more branding. So getting into project objectives. So I had 5 project objectives for this project. I wanted to learn about new engineering disciplines. Like I said earlier, I haven't really gotten into more than mechanical and a little bit of coding. So I really wanted to dive into the electrical side of it and things that I might be learning about in college, having kind of a background. Additionally, I wanted to research and solve problems on my own. So a lot of classes here at Grandview, we're working with teachers, and they're kind of directing us through every step. Mr. Combs, like you mentioned, he is there, he's great, but he is not teaching me anything. He's more directing rather than actually doing the project for me. So that was a big part of this project. Additionally, I wanted to effectively document progress so that I could actually produce a professional thing that I could eventually share with colleges. And then I wanted to stick with a plan and be organized. This is a struggle for me, as I kind of have issues with procrastination. But I tried to stick as best as I could to my timeline, which we'll get into right now. So timeline and changes. So my initial timeline was very simple. I kind of stuck with it initially. However, this timeline isn't 100% reflective of what I did because it has so many different components of engineering, from electrical to computer science to mechanical design, where all of it has to kind of mesh together. So it's not exactly partitioned this way, and I definitely did some revisions to my mechanical design down here, but in general, this is kind of how I went along my project. I initially researched components and purchased them, and then I was able to model them and create a waterproof case around the device. From here, I had to build and actually wire these components. This included 3D printing, soldering, all of that, which I will get into in a minute. And then I didn't plan for the data collection to actually require time. I thought it would just kind of happen naturally. So I added that in later as I got into the project. Additionally, I needed to create my UI before I actually collected this data because the UI actually needed the UI needed to be created before the data could be interpreted and actually analyzed by me. Additionally, I wanted to implement NFC, which I'll get into in a minute. That had to be cut out of the project, but I did learn a lot from that experience. Getting to the actual research of the project. So we'll start off with electronics. Like I said, this is all over the place because there's a lot of different components and moving parts. So if you want to know anything more about anything I researched, come over to my table right after, and I'll be happy to share any more additional details. So physical space for the components was a huge component because I wanted this device to go inside the cap of the swimmer, so it needed to be small and comfortable. So I initially began with the microcontroller. So the microcontroller was needed to be very small. Additionally, it is different from a microprocessor. I found that out because I was going to work with a Raspberry Pi, which has way too much processing power and drew way too much power from a battery. So the microcontroller was much more effective for this project. Additionally, I worked on battery types, so I needed this to be very compact. And I ended up using a LiPo battery. The other option I had was a coin cell, but the LiPo battery actually had built-in integration with my microcontroller. Additionally, it is rechargeable, so it cut down on the cost of the project. Next up, micro SD card and internal storage. I wanted to use internal storage just to minimize the space. However, I found quickly that the internal storage was only used to store the code that I actually programmed the device with, and not to actually store data that I collect with the device. So I needed to incorporate this thing. So from there, I actually created a wiring diagram shown here, which actually details exactly how to wire both of the components together using soldering, which you can see me doing right there. I definitely had a couple health risks. I inhaled a lot of lead, I'm sure, flux, and whatever else is in that solder. And then I got a lot of burns on my fingers. There's a couple scars. They'll go away, I hope. And then, yeah, so I soldered all that together and had to research SPI in order to create this. SPI is a way of transmitting data over using, I guess, 6 wires to send data back and forth between microcontroller and micro SD card unit. So additionally, getting into waterproofing research. This is more on the mechanical side of my project. I looked at a couple materials for 3D printing this, just to have an idea of what I'm going to work with that will be waterproof. So initially, ABS was the standout one. This is a typical 3D printing material available for most printers. However, it had a lot of issues with deforming and kind of bending, depending on weight. And then polypropylene. This is the material used in laundry detergent bottles. So it is definitely water resistant. However, it's very hard to print and not available to us at Grandview. Additionally, the final one I found was PETG, which is a polymer that actually that is actually hydrophobic and holds out water extremely well as it's extremely rigid, so it doesn't have as much risk of deforming and bending while printing. Additionally, I needed high accuracy, which was available with the PETG. Then the thick layers were very important so that in case water was able to actually seep through layers of the 3D print, it would be blocked out by multiple layers, so it can get through 1 or 2 layers of the 3D print, however not the entire case and ruin all my electronics. I wanted an IP68 rating on my device, which essentially means that the case is dust tight, as well as protected against continuous immersion in water for under like normal depth and not like scuba diving conditions, which seemed pretty reasonable given my project. Additionally, I looked into alternatives in case the waterproofing didn't work, such as silicone gels to actually case the microcontroller, or wax coating on the case to actually prevent leakage through the O-ring seal. Okay, so design achievements. I modeled all my electrical components and designed them into this assembly. So this assembly is actually the most compact design I could fit all of the components into. And around this, I designed the case model. So the case model, this is my first case model. It's very rudimentary. Have it on my table if you want to come pick it up and actually look at it. However, it was extremely tall, which did not fit, which wasn't comfortable in the cap. Additionally, it had issues sealing and being able to pull it apart, which is kind of important to actually get the components in and out of the case. So from there, I designed the second case model. I added this little notch, which aligns with a notch on the bottom, and it shows you if you are in a locked position or not, so that you know when you're able to open the case. Additionally, I extended the top a little bit just to add some more grip so you can twist it. And then I I shrunk the entire device itself and kind of flattened it into more of a hockey puck kind of size, which was much more comfortable in the cap. This is an exploded view. It shows just the assembly of how the parts go together and how the lock works. Okay, moving on to build achievements. So this is where I actually was able to 3D print and solder all of these components. So I 3D printed both the initial case model and the secondary case model. The secondary case model is this one on the right, or on the left in the clear. And as you can see, it is much shorter. It is a little wider, however, the compromise was well worth it. Additionally, I soldered the microcontroller. That's my soldering job. I know, I'm sure it's not perfect, but it gets the job done. And then I waterproof tested the case model, which I'll get into right now. So overall, I tested using a bunch of change, so coins that I wrapped in paper towels. And so essentially, the coins weighed down the case while I put it into a cup of water. And then the paper towel would allow me to know if there was any sort of leakage through the case without having to like examine the coins or whatever. Like it absorbed the water, so I knew right away. Additionally, so the results I got from this is that the white or clear case actually leaked through this bottom seal where I have my logo. This was an issue because the bridging between 3D prints actually deformed a little bit while it was printing. This was fixed later because I found that the blue case didn't have that same issue, and it actually is because the printing didn't have to bridge as far. Additionally, the blue case leaked through the seal because it didn't actually seal tight because the O-ring was too large. And then the white case was too small, so it actually leaked through the seal as well. So I kind of took the Goldilocks approach and put the two together and just saw if it would work. Completely out of circumstance, it worked, and it actually held out water for a 12-hour period. So I modeled my third and final case design based off of these dimensions, which is right here. So here's my final case model. I have a couple adjustments. So I edited the dimensions of the case for waterproofing, so it actually matched what was promising based off the waterproof testing. And I added a limit switch and a battery connection point, so that this has a lot to do with the coating, which I'll get into in a minute. Additionally, I removed the wall to fit the limit switch. So just it made for a much looser fit, and it was very comfortable to actually fit it in rather than having to squeeze and almost break things when I put it in the initial case. Additionally, I had to remove the NFC. This is just because it didn't work, which I will also get into in the next couple slides. So here's my data transfer outline. So this is a lot of the coding and where it came from. So I initially would collect data using the seed shell microcontroller that I chose initially in the project. This has an inertial measurement unit that is able to record accelerometer and gyroscopic data while the user is swimming. This is then stored onto an SD card while they're swimming. Because Bluetooth transfer does not work in the water, the wavelengths for Bluetooth are obstructed by how dense the water is, and so it is unable to actually transmit to a computer while you're swimming. So it is saved to the microcontroller, where I wait until the swimmer is done, and then it is sent over Bluetooth to the computer. And once the computer receives the data, it is able to convert it into understandable data that a swimmer can work with their coach on and interpreting. So connection research. This is where I had a couple struggles, but I initially researched near-field communication, or NFC. So this is the technology that is actually used when you tap your card or use Apple Pay. It essentially sends a max of 2 kilobytes of data, which was not sufficient for my entire thing, as a minute and a half of data actually was 616-ish kilobytes. So it was way too much information to send over a simple antenna. So I decided to kind of shift the project and use Bluetooth, but establish that Bluetooth connection via NFC. This was largely experimental, and I had to do a lot of workarounds to actually get this to function. So I ended up having to have a couple issues, which we'll get into in the next slide. So more on Bluetooth. So I use a version of Bluetooth called Bluetooth Low Energy, which is is kind of a new technology. And it is a direct device-to-device connection with the central or the client device receiving information and the peripheral or server device. I'll use those terms interchangeably throughout the presentation. But the peripheral actually collects data and sends it to the central device. Whereas the central and client device are able to receive that information and interpret and do whatever it needs to with it. So to make this connection, they actually use advertising information. So the peripheral device will say, hey, my name is whatever the device name is, and I have this information on accelerometers and gyroscopes. And then the central is like, I want to connect to you, because I need that data, and then it will be able to connect and transfer data through Bluetooth. Additionally, Bluetooth Low Energy, in the name, it saves power because it establishes the connection while data is actively sending. So the rest of the time, it is actually just waiting for a signal to be delivered between the two, which saves a lot of power and takes the strain off of the battery in my project. So this is getting into the NFC issues and just general data transfer issues that I had. So the first one was the seed shell microcontroller that I purchased. Actually had an update about halfway through my development of the code for it that was by the developers, yet it completely ruined the functionality of the microcontroller. I honestly don't know how it got rolled into production, but it rendered my device non-functional, and it took me about 2 weeks to figure out what the issue was, and I ended up having to roll back the board files to a previous version that I had saved on my computer. Then I worked with the Nordic NRF 52840 developer kit, which is the developer kit for the specific microcontroller in the device. So this allowed me to upload NFC code, but this was a much more difficult type of coding than I had worked with before, and so it was actually unable to send directly to my microcontroller, which I had to have this sort of pinout design, which actually would have worked hypothetically. However, this is way too much work for my project to just get the NFC aspect of the code working. So I ended up scrapping this idea and moving on to Bluetooth connection. So Bluetooth connection also had another issue where in concept it works, it connects, it sends data, it does everything I need it to do. However, the connection is very spotty between this microcontroller. So the data that's actually sent and received from it is not 100% accurate at all times. Additionally, NFC libraries were not included on the board when I was trying to implement NFC. So I ended up having to take this aspect of the project and postpone it to maybe this summer because it just simply was too much work to add in this 6-month period. Okay, so next up, getting back on track with data logging, I had a couple issues, or a couple things that I had to do for data logging. So I initially wanted to connect it through a serial port. So I wanted a second microcontroller that was actually connected to the computer to connect Bluetooth, which simplified the connection, rather than having to go into your system settings to connect the device to your computer. So this, you would plug the secondary Bluetooth device into your computer, it would receive information through Bluetooth, and then send that computer through a USB cord into a Python script, which actually put all this data into a comma-separated variable file on the computer, which then could be interpreted using machine learning and motion recognition via Edge Impulse. Edge Impulse was fairly simple to integrate, as all I needed to do was import data, split it into different sections of information. So say this is a stroke and this is a flip, and then the machine learning algorithm was able to detect the difference between the strokes and flips. Additionally, these libraries could be integrated directly into Python code, which will help with the actual display of information as I get into that later. So here are some coding achievements. Initially, I collected some initial accelerometer and gyroscope data using my microcontroller. This is just me moving it around just to see if the actual sensors are working and allocated correctly. Additionally, I coded the NFC tag to send devices to my website. This is more of a proof of concept, as it sends you to my website. This capability can be used in the future to establish a Bluetooth connection between the microcontroller and the device if I wanted to work on that information. Yes, so next on to, it's not clicking through. How will we do that? Okay, so next I coded the central device, which is a device that is connected to the computer. And then, so that essentially took in byte data from the characteristics and advertising information that it received on the peripheral. And then it turned it into string data that is actually readable by the computer. And then I coded the complete peripheral. So this actually collected data, saved it to the file, and then sent it over Bluetooth. So right here you can see the actual devices in the case. It's kind of faint, but there's a red light in the case. That is indicating that the data is being collected, and as soon as the case is removed, the microcontroller will be turned into Bluetooth sending mode, which essentially allows it to connect and then transmit the data as intended. So next I got into GUI development. I created a graphical user interface to display the stroke and breath information. Initially, I designed this to connect the serial, so connect to the central device, and then tell you if it's collecting the serial data properly, as well as make a graph out of the data that it collects, which is shown here. This is actually my initial swim data from my test with the device actually strapped to my head. So I also connected the serial device, which allowed it to actually transfer data via Bluetooth, and then eventually I'm intending on adding an interpretation code. The interpretation code actually works, which I'll show here. However, I need to still implement this into the GUI, as I honestly ran out of time on that aspect of the project. So here's a quick, my swim with the device. Let me make sure that the volume's down. I think it had something. We're going to put it on 2x speed because it takes about a minute and a half. But this is actually me with the device in, shoot, messed up. This is actually me with the device in my swim cap. I'm swimming throughout this thing. Throughout this video, I swim, take 3 flips over 4 laps, It's about 60-ish strokes. And I took this data that I collected from the swim and graphed it, as you can see here. So each individual orange line, they're kind of small and hard to see. However, each individual orange line is a stroke. They're very rapid movements, so it's kind of difficult to see on this graph. However, the computer is able to interpret that as a stroke. Additionally, each yellow dash is a flip in the data, so it indicates that I have flipped and turned around and began to swim the other direction. So with this, I created a machine learning algorithm, which actually had 100% accuracy at deciding whether a motion was a stroke or a flip. So you can see here, this location is the uptick on a stroking data, and this is a downtick. So it's able to differentiate the two as well. I just didn't think that was as essential because you can count how many left strokes you have compared to right strokes based off of simply cutting the stroke amount in half. Additionally, right in the center, these are flips that were differentiated correctly, and actually it could tell the difference between all three of these motions, which allows the swimmer and the coach to understand how many strokes they took and all this information, which is kind of the culminating idea of the project. So I was able to design this in order to, so the swimmer could understand what they need to improve on efficiency-wise. If they're moving efficiently through the water, they're taking enough strokes, maybe they're taking too much, and so they can improve with the help of their coach in the future on those kind of statistics. So thank you all for watching. I will take any questions at the moment. I'll have my bibliography sliding through in the background. So, first question.
Did you ever think about using a kinetic power source?
I did not think about that. I thought that the battery was the simplest way to actually integrate it to the project because it's rechargeable and all that.
How long is like the battery life?
So I haven't actually tested the battery life, but it lasted sufficiently through the swim and the transfer of data. I haven't had it die yet, so
Since you bought it?
yeah, since I bought it. So I mean, I haven't ran it on the battery too much. However, it didn't die while I was using it. Sam in the back.
For different strokes, like breaststroke or backstroke, does it work the same between now?
Yeah. So for other strokes, that implementation can be added later. Yet it will still collect data for all those strokes, but it doesn't have the interpretation to actually understand what is a stroke, what is a flip, all that stuff for those other strokes. I don't know your name.
I know you talked about PETG and ABS in your printing, but did you ever consider like a resin print so you didn't have the gaps?
Yeah, so I did consider resin print. However, it was kind of a lot more work, and I didn't actually have access to a resin printer. So I kind of went with the what we had available, which still performed just as well as I needed it to.
So your machine learning algorithm, was that like pre-trained or did you train that yourself?
Yeah, so I used my swimming data that I actually collected and trained it based off of. I said this is a stroke when it was an upstroke, and then this was also a stroke when it was a downstroke, and then the kind of yellow tick marks in the middle. I said that is a flip, and it was able to delineate based off of the kind of information that I had trained it with. In the back.
When you were training your algorithm, did you have other swimmers help participate in training the algorithm just in case they're differentiating factors or computers?
Yeah, so I actually intended on doing this. I honestly ran out of time. I was able to actually collect data just like 2-ish weeks ago, so I wasn't able to effectively like get data from everyone or like a bunch of people and then also interpret it and present on it. So that is something that I want to work on in the future, but in general, the stroke itself is very kind of rudimentary for especially for freestyle. It's very simple, and there's not too much variation in head movement, at least. There are definitely different ways to swim, however, the head movement typically stays the same between swimmers. And that's some of the information I got from my advisor as well. Any other questions?
All right, thank you, good job.